I'm so happy, Marie, that you're able to make this and give this talk on an incredibly complicated and exciting field of quantum computation. You've managed to just distill everything down, I've seen from your slides. So I'm looking forward to your talk.
Okay, thank you. Thank you very much. Invite me here, and I'm very excited to listen to all these lectures. And I'm going to speak about quantum computing or quantum computation, and it's a very big field, and I'm working in it. I'm working in a very small part of the field. But I anyway have tried to capture the whole field, and instead of going to detail, I have instead tried to give a little bit of everything. So, I don't know, it's very basic, there are no equations, and I might also finish very quick, I don't know, if there are no questions. And then maybe we can have a discussion instead. And I really try to make it basic, so I really want stupid questions. And I'm not sure I can answer them either, but then I have Ray Laflamme. I already noticed him that he should be able, he should help me. And I can say also when I did this talk, every subject I looked into, Ray had a very significant paper on that subject. So I think you are one of the experts, absolute experts in the field, so I'm very happy you're here. So I should also introduce myself. I'm at Uppsala University. I'm a researcher there. I did my PhD in Uppsala, and then I went as a postdoc to Ray one year, and then I've been in Cambridge 3 years, and I've also been in Urbana-Champaign in Illinois 1 year. And I've been working mostly on theoretical, looking into the theory of quantum mechanics, you can say, like entanglement, the geometry of quantum mechanics. So I'm very interested in quantum mechanics itself, but of course it's amazing that it has applications that you will be able to use later on. So yeah, that's who I am. So first I want to tell you a little bit about the history, or actually that was I should also say that I got to know very late that I was going to give this talk. So first I wrote an abstract and then I wrote a talk. So everything is a little bit upside down. So first I wanted actually to talk about quantum mechanics. Maybe it's very basic now, but I wanted to start because quantum computer really they really use the features of quantum mechanics. So I think we should all in the room here understand what it is first. And so it's actually how the world looks from an electron's perspective, or like if you go to very, very small scales, how will the world look like? So it's the theory that describes atoms, electrons, photons, and other microscopic particles. We need to use this very special theory called quantum mechanics. And I think this particle wave duality tells very much also what quantum mechanics is. And this is this double slit experiment we heard about in the morning. You can do it also with electrons. You can do it with light, and then with light you have a feeling that it has this wave character. But actually light has also a particle character. But then what they could see was that also these particles, the electrons, have this wave character. So that if you have this, you have a double slit, so you have like two holes, and then you shoot electrons in here, then you will see then actually that you get single counts on this here, but they will actually add up then, so you have like more, electrons in some parts. You will see the wave behavior here. Okay. So you have actually this wave-particle duality. That you have a particle with a mass and a velocity that can also have property of a wave with a wavelength. This is I have some equations I had here, but and this the whole system, the quantum system, then that both have this. It's described by this wave function, and in this wave function, all these properties are contained, and you have both the wave and the particle properties in here. And then actually it's only how you design your experiment or how you detect these particles that depends then if you measure the particle behavior or the wave behavior. And this wave function here now too, it's can you see anything? It's not actually, I don't know, it's been a debate also if it's a real thing or not. But actually what we see in the nature, now it should be, it's the square of this wave function that give actually the probability where to find the particle. So this we call probability amplitude, this wave function. Okay, I just wanted also to tell you a little bit about different problems that we have in quantum mechanics. But we have this measurement problem that is very problematic. It's not until an observation is made that it has a yeah. So it's actually quantum mechanics. You have one theory that describes this wave, how it goes, but then you basically have no theory actually about how you get these measurements, these probabilities. So this measurement problem is a big problem in quantum mechanics, and there are many ways to try to interpret what's happening. But I don't know. I just added. I can take away. Yeah. So you have this. That the theory is probabilistic theory, and then you have also this quantum superposition. So you can be at two places at the same time. And you can also be in two different energies at the same time. So if you have atoms here, you can be in the ground state and the excited state. Here are some atoms here. You can be in ground state and excited state at the same time. And this is a way for some people to how to view it. It's actually like something that is there at the same time, but it's how you observe it is what you actually. You see. Okay, and then this superposition is very hard to understand. That's also we saw in the first talk this morning. That we have what happens when we have macroscopic objects like a cat. Can a cat be in superposition or not? Yeah, maybe it can, as we saw in the morning. An entanglement we have also in quantum mechanics is spooky action at a distance. Yeah, and all these things that I talked about now, it will come together then in this quantum computer that I will talk about. So we will start now to get into the world of computation, and this was in 1943 that people or someone at IBM thought that there might be a market for 5 computers in the world, and that together with this, that we had this supercomputer that weighed 30 tons, and they were thinking maybe in the future it can be as light as 1.5 ton. And I think this also put a setting on where we are. It's very hard to predict the future, and also for quantum computer. So what is happening in this information technology is that everything is getting faster, smaller, and then faster. So we have shrinking computers, so the processor now in computer, they are very small. They are on the nanoscale. And then, but if we want faster and faster computer, even faster, we will at some point hit the quantum level. And then what will happen then? So can we use it somehow? So the first step towards quantum computing was actually taken in 1968. No, there was when they started to look into reversible computation, because for a normal computer, the problem is also the heat, that you have a lot of heat dissipation. And normal computer, they have also this irreversible gates. That's why they produce a lot of heat. So in 1961, there was a principle, Landauer principle, that was described by Rolf Landauer, and that irreversible computation. He actually saw that they will the loss of information in them, that you have, for example, in the computer, you have 2 input and 1 output, so you cannot trace back from the output, you cannot see what input you have. That will actually make the entropy increase and energy is dissipated. And in 1967, Charles Bennett proved then that it's possible to build a universal computer from reversible gates, for example, the Toffoli gate. So this is actually the foundation, because quantum computers are also reversible. So this is one of the foundation, the first steps towards a quantum computer. So what is a quantum computer now? It's a computational device that uses quantum mechanics to store and process information. And it solves some problem more efficient than a classical computer, for example, factoring large numbers. And I made these sum problems here so that it's not that it's just this magic machine that will come and solve all the problems we have much more efficient. It's only like some problem where we have efficient algorithm. So, but these problems are very important. For example, this factoring is a very important problem because we have a lot of security. We have a lot of encryption that is based on this. So factoring large numbers. So the algorithms we have are very important. So, then we can also use it to simulate quantum systems, which can be used to better understand, for example, chemical and biological systems. So that's, I think it has a lot of great application, even though it's not, it will not, we have still a lot of work to do, not only on the, to manufacture one, but also to look into the theory, what it can do more. Okay, so the first who were thinking about this was actually Richard Feynman, and then he was first he was seeing that that actually he was looking into what can happen if the computer elements get smaller and smaller. Can we gain something from it? And then in 1982 he actually considered then that a quantum computer can actually be very good for simulating a quantum system. But then there was 1885 that David Deutsch described the first universal quantum computer. And here I would like to stress also that you can then see that that any physical process can be perfectly modeled by a quantum computer. And then that shows actually that a physical process is, and computation are very linked together. And this computation is not only something mathematical that we have, it's actually like a physical process. This is very important. So if we have like now, if we go into the quantum, we have to see then what are the computation, the processes, what are the computation we can do. So, and for example, this is something you can see also logic from physics, that if you have this beam splitter, a beam splitter that is like it's a hot silver mirror they call it, so that if you have a photon coming in, or this is a light particle coming in here, you would have 50% probability of being reflected and 50% probability of being transmitted in this beam splitter. But then if you put two of these together, if you have two beam splitters like this, and you put in a photon here, so from the previous picture you will think that, okay, half the time the photon is here and half the time the photon is there. But actually what you will see when you look here is that, now this should be up here, the photon will always 100% of the time hit this detector instead. And I think this is actually in the first talk in the morning that Einstein was thinking about also, like that, how can this be? Why? Where is the photon? Is it here or here? And this is actually what quantum mechanics is all about. It's both in this and this. It's in superposition between both of these. And if we now can think about this as a logical process now, that you have something, we call all these horizontal lines at 0 and all the vertical lines as 1, we will see that the 0 goes to 1. If we would have a particle coming here, it will go to 0. So we can call this a not gate. But it actually built up with two identical objects here that we can then call, you can actually say it's a square root of naught. So you have some new logical element here that you didn't have in classical physics. This is actually something new in quantum physics. And then you can see this is the founder of classical computing, Alan Turing. And he's asking here, why should I accept this logical impossible operation? And then Bohr and Einstein, they were talking a lot. It seems like they said we have to accept it because it existed in nature, so it's something that's there. Okay, so what now? What is now a quantum, a qubit? What is a quantum computer? What is it made out of? It's made out of qubits. And if you compare them to a classical bit, in a normal computer you can have a 0 or a 1. In a quantum bit or a qubit, you have this superposition that we saw before this in this interferometer. And if you have many qubits now, you have a classical register here that can represent the number. In the quantum register, you have then a superposition of all these different numbers. And and then you can, in this way, you can create entangled state. And then what is very very nice then is that if you have many qubits, you can encode much more information than if you only have bits. If you have only only bits. You can only encode one number at a time. But the qubit, it encodes two numbers. You have the two-way, like the 0 and the 1. And then if you have n qubits, you can encode them 2 to the n number. And that grows very fast. But if you have then n equals to 1,000, so 1,000 particles, 1,000 qubits, that actually have more information than the number of atoms in the universe. So 2 to the 1,000 is like 10 with 300 zeros after it. It's a very big number. And this is called, the quantum parallelism that we have then in our qubits, in our in the quantum computer where we have all the qubits now. We have a lot of information that we can actually process in parallel. So that's one of the powers of a quantum computer. Then we have the quantum gates. Because now on this qubit we want to do some operations now, to actually do some algorithm to get some answers. And the quantum algorithm is built up of these gates, and you can actually think that if you have like 100 qubits that you maybe need to do gates on all of them, but actually you can see that you can choose the gates from a universal set of gates. So you only need actually 1 qubit gate and 1 2-qubit gate. That's what you need, and then with that you can do a universal quantum computer, quantum computation. And how they look like. So first we have this Hadamard gate that can also, you can see as this beam splitter that I talked about before. That you go from 0 and you go to a superposition 0 plus 1, or you have a 1 coming in and you go to superposition 0 minus 1. I should also tell you that in front of this 0 and the 1 you can have complex numbers. So here you have a minus, but you can also have any complex number there. So that's one gate. You have the Hadamard gate. And then you have this control NOT gate. So you have a target and a control bit. You have 2 bits coming in here. And it's maybe hard to see here. But depending on the control target, if the control target is in 1 there. No, if the control is in 1, you will flip the target. So you see here, if this is in 1, you will flip the target. So this gate, and together with the phase gate, I didn't draw it here. You just put the in the phase gate. You just put a phase if you have a 1 coming in. With this, you can do any operations that you want. Okay, and then after you've done these gates, you have a readout. And this is also very important to understand. It's not only that we have this, maybe sometimes it's easy to feel that this quantum computing is only this parallel, that you have you encode all the information and you just do parallel processing on all this information. But that's not the whole story. The story is also that we have a readout. And the readout, what we saw before, if you measure a quantum system, you actually collapse it into one of all the possibilities that you have, and you have then a classical output. And but the most important thing here is that this algorithm that we create, it has to increase the probability of getting the right answer. And then we use this quantum interference that I talked about before, and And these parallel answers, this quantum parallelism that we have, they can be viewed as waves, and they will interfere and enhance the right answer. And that's the way. That's why you can't say that all the problems you can just solve quicker on a quantum computer. You really have to find the right algorithm in a quantum computer where this is possible. So it's not enough just to encode parallel. Yes.
So if you have 8 qubits, if you do the measurement, you can only extract 8 bits, correct?
Yeah.
But you can also entangle those 8 qubits with the large number of qubits and then measure all of them. So in principle, you can extract more than just 8 bits, correct?
But if you entangle, if you measure something, you break this entanglement. You don't have. You lose the.
But the question is it in principle possible to extract this 2 to the 8 numbers? No.
No, so the only thing you can do is actually only to enhance the right answer. Okay, this was what I did, and yeah, this you can also see.
Can I ask a question? Just
Yeah.
before you go on? So you said earlier that David Deutsch described a universal quantum computer.
Yeah.
So what does universal mean in this context?
Yeah.
Because I'm a bit confused how
Yeah.
you said earlier that quantum computers they're great at answering some problems.
Yeah.
And yet David Deutsch talked about a universal quantum computer.
Yeah.
So does this refer to your last point about how only when you read something out, then that's what limits the kinds of problems that you can do, even though the computing bit can be...
Actually, like a quantum computer can solve do the same thing as a classical computer. But actually, when I'm talking about that they can only be more efficient in certain problems. So when I say universal computer, it's actually they can do all the computations. But this algorithm, you have to make.
Got it. Thanks.
Okay, so here you just see how you have to many steps. You have many answers that's parallel, many solutions here, like maybe in the end of the computation. But you want then the probability of the right solution to actually be increased. And of course, I should also say that the quantum computer is a probabilistic. Everything is you cannot only run it once and then get the correct answer. You have to run it many times and then see that most of the And then you see also it depends what problem. I will discuss that later too, like what kind of problem you have. But some problems are easy to check if you get the right answer, for example. Then you only need to do it once, of course. But it depends what you are after. Okay, so this is just also a graphical view of the computer. This is like the qubits coming in a superposition, and then you have some processor here, like here you have the gates.
It's quantum.
Superposition of all the slides at the same time. And then you have all the answers coming out here, but then of course you need to read out this, and you need to see. So this will give you an understanding of how it works. And now I wanted to talk a little bit of computational complexity theory, because as I said, there are only some problems actually that the quantum computer will do more efficient than a classical computer. So I would like to, and we have to see what where this problem fits, and what is computational complexity theory? It's a theory that where you talk about how does the number of computational steps scales with the size of the problem. and we want them to classify all these problems according to how hard they are. Like, will it be, how much harder will it be if we put in much more qubits, for example, or much more bits? How hard will the computer, how much more computational steps do we have to do? Like, how much longer time will it take? And we can say that if an algorithm grows polynomial, for example, n squared, so this is the number now, n is the number now of bits or qubits, or it is assumed to be efficient algorithm, and we also call it that it's in the complexity class P. So in a normal classical computer, everything that scales polynomial, we say that these are problems that we can solve on a classical computer. For example, it's multiplying two numbers, or all these normal operations that we do on a classical computer. They are in the class P. So, for example, like if you have this n squared, you can see how it grows now. If you have n 1, 2, 3, 4, 1, 4, 9, 16, 25, 36, 49, 64. If you compare this now to something that grows 2 to the n instead of n to the 2, like then you say it grows exponentially. You have the n in here in the exponent here. It grows then. It grows much faster, as you can see. Like and it will grow even faster. And this is exactly the same thing as I told you about also the qubits. That number of qubits. Then the information we can encode grows exponential. So this is something that explodes.
N is the number of bits?
Yeah, or qubits. Or, yeah. Okay. So we have now described this complexity class P, and there's a lot of text here. And this is this green. I don't know if you can see it here. This is this little green dot there, and then we have another class which is called NP, which is non-deterministic polynomial time, and that is a class of problem where the solution can be verified in polynomial time. So, for example, a good example is this factoring number problem. Because if you have a very big number that you want to find the factors of, if you have two factors, it's very easy to check that this is actually the solution to the problem. So that is a typical NP problem, factoring of large numbers. And then we have another class, also NP complete problems, and they are the hardest in the NP class. And if you find an algorithm to solve such a problem, NP complete, you can actually, if you find an efficient algorithm that actually will make these NP complete problems to belong to P, they will be efficient is that they will scale polynomial instead. Then actually all this box here will go into P problems here. It will just be so they are very special problem, this NP complete, and they are, for example, one example is this traveling salesman problem. If you find the shortest path between a set of cities where the path goes through each city once, so that's a very hard problem if you have many cities. And then in this computational complexity theory, this is a very big question, like is NP equals to NP or is it not? And they believe that that we will not find any efficient algorithm to for this NP complete, but we don't know. So this factoring, for example, is not proven that it might be NP. We don't know, but most likely it's actually P is not equal to NP. So the problems here in NP, they have on algorithms growing exponentially with the problem size. And then, so this was all like now classical. Yeah, this was all classical computers. But now if we have a quantum computer, we actually have an algorithm that solves NP problem, factoring. So we have actually, for a quantum computer, we can actually solve problems in this region. And of course, we can also solve problem in the, as we can simulate a normal classical computer. That's very easy for a quantum computer. So, and those problems are called bounded error quantum polynomial. The problems that the quantum computer can solve in polynomial time. And you have also the problems that quantum computer cannot solve. They are called QML, QMA. That's outside this AQP. Anyway, so what this shows is that the quantum computer is in this area. So, for example, this traveling salesman problem, it cannot solve efficiently. And there are many other problems that it cannot solve, or at least we don't have an algorithm for it now. So, so just to see that it has more power than a classical computer, but we don't know how much more power it has as it is now. Okay. Okay, so I wanted just to talk a little bit of quantum algorithms. Quantum algorithms also. So an algorithm is a sequence of instructions the computer should perform, and the quantum algorithm, it uses superposition and entanglement, the quantum algorithm. And it usually describes a quantum circuit acting on input qubits. So usually we talk about these quantum circuits, but as I will show you later on, there are other ways of doing quantum computation. Not with these circuit models, but other things. So, and I will just discuss some algorithm here now. So first we have the Gruber's algorithm, which was found in 1996. It's a quantum algorithm for searching an unsorted database with n entries. And here you can see that it's a quadratic speedup compared to classical computer. And it grows linear with n on a classical computer, and now n is the bits, and n squared, these are the qubits on the quantum computer. So actually both are in complexity class P here. So it is a speed up, but it's not that we go outside the complexity class P here. So, but still it can be very helpful. But the most amazing algorithm is actually this Shor factoring algorithm that was discovered in 1995. And here there is an algorithm that can factor integer number in polynomial time on a quantum computer. For example, you can find that 127 times 229 is 29,083. And this is a very small number, but imagine that you have maybe like, several hundred digit number. It's very hard to find the factors. And what this has been...
this is an NP problem, NP complete problem?
No, this is an NP.
This is a polynomial? NP.
NP, yeah. Exactly, this is NP. Yeah, no quantum computer can solve any NP complete problem as it is now, for now. So quantum computer can only solve n problem in NP. And this is it's exponentially faster than the best known classical algorithm. So it's in NP, but it's also in BQP, yeah, because it's solvable with a quantum computer. And it has been implemented on a 7-qubit NMR quantum computer to find the factor 3 and 5 of 15 in 2001. But I think I saw also later on there are more papers. I think they found 3 times 7 is 21. And some other more progress on this. This one. Yeah. Thank you.
Remy, can you clarify just to follow up that question, the difference between P, the larger group of NP, and NP complete? What makes something NP but not NP complete and still not P?
What did you say?
Well, how could a problem be outside the P but not in the NP complete? Yes, in that region.
Ah, in this region.
Yeah.
Oh, okay. Yeah, there are. So this problem. Yeah. First of all, if you have a solution to this, then you have a solution to all. They have a very special property that these problems in NP they don't have. If we would find an efficient algorithm, classical algorithm for factoring number, that would collapse all of these problems into P. That is only if you find the solution to this NP problem.
Okay.
So they are very special, like these NP complete problems.
But it's still, as soon as you're outside that P problem area, it's an exponential algorithm that you need.
Yeah.
Okay.
Yeah. For today, we don't know of any other, like, yeah.
But still, what is special about NP complete that there is not, that is not in NP? The special area of NP complete.
Yeah.
It's harder than the other NP problems.
Yeah.
In what,
Yeah, they are harder than the other. Exactly, they are the hardest problem here.
not mathematically, but in what way?
In what way? I mean, if you see this, the traveling salesman problem and things like, I think it has like the optimization problem is extremely complicated, like to find the problem. Yeah. So it's, and there may be other people who have better answers.
I don't.
Salesman.
But you can't tell right away by just looking at the problem that it's NP or NP complete. I mean, you have to.
Yeah.
I mean, it's
Yeah,
not
you-
obvious.
No,
right
it's
away.
not obvious. No, there are like certain problems that people formulated that they saw that this is
So you think that,
have a relation to this, which is an NP complete. I mean, it's a very not.
So your bullet points there suggest that the distinction is if it's just NP, you can verify them in polynomial time, but the NP complete you can't.
Oh no,
Or,
no, you
or
can't.
anything in NP can be verified in.
Oh yeah, that's
Polynomial
true.
time.
Yeah.
So I guess the confusion that probably you and I are both having is the NP complete requires an exponential algorithm. The regular NP requires an exponential algorithm.
Yeah.
So what makes the NP complete harder? Because they both require exponential algorithms. They sound like they're the same.
Oh, okay, yeah. Yeah, it's a good question. I don't know.
Okay.
I mean, merely in terms of how to use language, if one would strictly limit oneself to problems one has solved and only start from clear solved problems, whatever kind, could one from there on develop all these languages and all these classifications? Or are these classifications largely within unsolved problems, so they are not really we cannot, we talk about things we don't really have.
Yeah.
Or can you give one example of a solved problem which is not just an inverse kind of thing? I mean, you can build something and then do something with it, and you cannot do it with another computer, and then you say, well, this can do something the others cannot do, but we have constructed it by definitions. So, do we have it?
So you mean like a specific example?
Yeah,
where-
can you give one case which is really clear? I mean, not just a factorization thing. I mean, there are wonderful examples of autistic persons. When you go into how they do things others cannot do, they do it with associations we just don't think about. And here, this similar kind of thing could psychologically happen. I cannot exclude.
That sounds like a very long discussion. Why don't you have that after?
Yes, sure. I just want to raise it. Do we know what we're talking about?
I was just going to say that since everyone was having this big discussion, I did. The one thing that I actually read of the required reading this was the limits of quantum by Scott Aronson, and in that I think I was finding the whole P, NP, and then NP complete really confusing too. And he says that the idea of an NP complete is that if you find an efficient algorithm for any one of the NP complete, then you would find the solution for all NP problems.
Yeah.
That's it.
Yeah, but we don't understand what
Why
differs.
is it harder?
But that's what makes it NP complete, that if for this set, that's all he says. That seems to be the basic property, that if you find a solution for that, then everything becomes solvable. So that's it.
It's not a complete answer.
That's the thing he gives.
No, but I can see like you have really problems in here that if you solve all of them, I mean, if you solve something out here, for example factoring, it will not collapse everything into P. But, so these are very special properties, which that's why they are grouped together. But you can't say, yeah, I told that they are harder, but maybe that's not right to say. You shouldn't say that they are harder. They are just different. These are different than these. Maybe as you say, they are all exponential. Like they all.
Maybe they are not
Maybe they are.
reducible.
Huh?
Maybe they are not reducible to polynomial. And the others.
Oh, that's no, but you don't know anything if they are reducible either. That you can't say anything. Yeah.
Would it be fair to say that what makes NP problems complete, what makes NP complete problems different is that any other NP problem can be reformulated as one of the NP complete problems?
One more time.
So, are NP complete problems special in the sense that any NP problem could be reformulated or recast as one of the NP complete problems? And then once you've solved the NP, once you find an efficient algorithm for the NP complete problems, you can recast any NP problem, any other NP problem, as that NP complete problem and solve it. Would that be
I mean,
close
this
to
is
right?
That's my understanding of it.
That's
Although
what they
I'm not a
say,
computer scientist.
That's the,
But that's not one. But I think that might take more.
It's true. It makes sense.
I don't really work on this, so I just like know the notions of this.
Can I ask a question about Shor's factoring algorithm?
Yeah.
Why only 15 and 21? I mean, what's the limit? If you've got 2 to the 7, if you've got 7 qubits, you're looking at 2 to the 7 solutions at once.
Yeah.
So why can we only factor 15 with that? Or why did they only factor 15 and 21 and not much bigger numbers?
Because you have, like, if you have 3 qubits, for example, then you can have 8 numbers in that. So, and then if you have one more, then you have 16. I don't know. I think how many qubits did they do it?
You said, I think it said 7, so you should have 128
yeah,
numbers.
that's true.
which-
Maybe Ray knows this thing.
So, the way that it's solved, you have to do something called a Fourier transform and some other pieces. It's not just enumerated all the numbers. You have to do some operation, and these take some qubits.
Okay.
And if I would have a really good memory, I would tell you what is the number of qubits you need to factor a number with k bits.
Right.
It's a polynomial, but I don't remember exactly what's that. I think it's k to the cube, but my memory might not be. Don't quote me on the cube.
But that's good enough. Thanks.
Yeah.
Yeah, so this, so what this Shor algorithm can do is actually they can break this, the public key crypto system, which would be very bad if we couldn't use that, which is also one of these RSAs, data security is one of the techniques we use on the internet when we do transactions. So what would we use instead? How would we have secure keys?
But not all public encryption is broken yet, right? So there's still some
Yeah.
algorithms.
There's another, yeah, that's true. That's true. But also what we can do also is that we can use quantum cryptography. Maybe. Okay, and then another application also of a quantum computer is actually simulating quantum system, what Feynman said in 1982. And if you want to simulate a quantum system on a classical computer, it will grow exponentially with the problem size. So of course, if you have a quantum system, it will be much more. It would be much better to have a quantum system to simulate. And then you have in 1996 actually. Seth Lloyd showed that quantum computer can simulate local quantum system efficiently. And then you have also like experiments with up to 6 trapped ions have been used to simulate local quantum systems. So there are also like a lot of experiments going on in this field. Okay, so I wanted just to summarize a little bit. Like first, let's say that computation is actually a physical process. So if we have a new physical laws, like quantum theory, we actually have to see then what is the computational power in this theory. So it's not something fixed. And then something also I wanted to stress is that the quantum computer can solve some problem faster than a classical computer. And we still have a lot of research on this, both finding new algorithms and then also like
This is the final collapse.
yeah. Okay. Yeah, I think that was it. Oh yeah, okay, and the last thing I wanted to say also that the quantum computer cannot solve NP complete problem, like the traveling salesman problem. I mean, just to stress this, because I think what I saw in a lot of on a lot of articles that I saw on the internet that it's very easy that people put easily up that quantum computer can solve NP-complete problems like the traveling salesman's problem. That's not true. So that we should also.
It can solve them. It just
not
it can't solve them more efficiently than classical.
Yeah, okay, yeah, that's true.
Do you mean that it by definition cannot solve them, that or that you
More
don't
efficient.
have any proof like in Peter Shor's way? Are we in a situation that it will never be possible to do it in
No.
or they just don't know?
We just don't know. Yeah, we don't know. Maybe there will be. Yeah, just right now we don't have quantum algorithm for this.
Okay.
Okay, so this is just so that when you report on what the quantum computer can do, like just be careful, like not to claim too much or. So that's something. Yeah, that's it.
Great, thank you.
Yeah.
So I've been keeping track of stoppage time, and she was actually right on time, perfectly done.